every kind of change you do, just do it in a branch and then merge it later on. It's very easy to bug fix and refactor stuff, especially stuff you ship to customers, or like a special version you ship to a special customer, which turns out to have a problem, and it turns out that maybe the compiler is broken, for example, and I can still trace that back 3 years later because I have the whole tool chain, the whole build environment included in the source control. What's pretty interesting as well is when I upload firmwares into this patch manager, I have a script that's going to tag it, and then I can just say, yeah, did you download it from the patch manager on this day, which is the ID, and go back and kind of check bugs out. I'm going to go into more detail in the whole debugging part of the talk. And another Agile technique I use is unit testing, which is actually kind of complicated to implement on the hardware device because test suite are normally a whole big amount of code because you have like all these test cases. So it doesn't fit on the device usually, or you can fit like 50 tests on it, and then you have to reflash it and then execute another 50 tests. So what I did is build mock objects for basically every kind of hardware feature there is on the device using C++, which I'm going to go in later on. So I have like a virtual MIDI interface, I have a virtual encoder, I have a virtual timer, and I can basically execute most of the unit tests on the host itself, so it runs in a few seconds, and I can see when I'm doing refactoring that maybe the latency of the MIDI protocol parser is not going to be good enough, for example. That's really, really useful for refactoring. Like when you start to have this big framework, you spend most of your time just slightly redesigning APIs, for example, or replacing an object by another, and it's actually pretty crucial to execute it. One thing I'm working on is using a simulator to basically execute the whole test suite and like log different stuff inside the simulator, so it runs in a few seconds, and I still have the hardware approach, the real one. And the last part of this whole Agile stuff was basically project automation. Like I have this big code base, and I'm at the moment the only person working on it. And every time I do a change, I basically have to update 20 different firmwares and tag it and update the documentation. So it's actually pretty cool to use an automated system like BuildBot. With every time I do a code, it's going to regenerate all the firmwares, regenerate all the documentation, run the unit tests, and basically update the patch manager as well. A pretty cool thing is using this information as well to plot different parameters of the firmware, like the code size over time, so I can see which revision just added a few kilobytes at this part, or which revision just destroyed the latency, for example. Because I can plot all these kind of hardware-specific information and store it as well. So that was basically a short overview of the whole Agile stuff, and you can check out the scripts in the GitHub as well. And if you have any questions, you can ask me later on. So I'm going to go over to the C++ part. Who thinks that C++ on an 8-bit microcontroller is like a heresy? Because that's a view you find pretty often. It's one I had as well, because I come from assembler programming and C programming. And it was like, oh, C++, it's just going to be awfully bloated. And actually, it is. It's like C++ is kind of this monstrous language. It has like 10 different sub-languages. You have like a normal C part. You can write C in C++. Then you have like this object orientation part. You have templates, and then you have like exception and a whole kind of exception mechanism. Then you have STL and like memory allocators and operator overloading. So it's basically like this big octopus with like different kind of languages waving around. And if you try to use them all, like there's a few books like Modern C++ Design. It just makes my head explode when I go to the second chapter. Can we turn the lights down, or is that on purpose? Anyway, it's like this multi-paradigm language. But what I learned to love about C++, like coming from Lisp as well, was like what is this object orientation where you have to use virtual if you want to overload a method. It actually makes sense if you look at it from a pretty hardware-near point of view, because you can basically control exactly which byte of the memory is going to be used by what, and how function calling is going to work, what the overhead that's implied is. And it actually makes kind of a lot of sense. And if you're pretty careful and the compiler is good as well, you can basically produce code that's pretty much what you would have written in assembly. That's what I built this ring buffer with a template to generate like ring buffers of different sizes and of different memory types. And basically, you're pretty careful when designing ring buffers to have like a size that's a multiple of that's a power of 2 to be able to do like modular arithmetic to do masking for the modular arithmetic. And when I first built this template in C++, this ring buffer with a template in C++ and looked at the code, and it was actually better than what I had written in assembly, I was like, this is perfect. I just need to write one line for a new ring buffer with a different size, and it's pretty much exactly what I wanted. So I settle on a subset of C++, where I basically don't use any kind of dynamic allocation, like there's no new, I just do it with static initialization, which has its own kind of problem. I'm going to come back to that. I do use multiple inheritance because that's pretty useful when you build a GUI framework, and using callbacks, you can just like inherit from this callback class and are able to pass it around with static type checking. I use method overloading pretty much as well because you have like pages or encoders that are going to be included in containers, and then it makes sense to have like virtual method. And in this case, like when you use a virtual method, it's going to add a function pointer table to your class. And it's going to add a separate lookup before you do a function call, a method call. And in those kind of cases, in C++, in C, you would have used a function table, so you would have done exactly the same, basically. And what I use pretty often as well is templates for data structures. I don't use templates for any kind of weird compile time pointer voodoo or stuff like that, but that may be something I have to look into. Templates are still like a bit of black magic for me. But the biggest advantage of the whole thing is basically object orientation. You can encapsulate functionality behind objects. So, for example, the whole hardware elements of your microcontroller, the serial UART, for example, or the LCD connection or the SD card, that they are all wrapped in objects. I basically just need to instantiate I just need to subclass it to adapt it to a specific device. For example, if I have 2 serial UARTs in C, I will always have to kind of build a specific structure, and then it's just all easier to do with objects, basically. And you can, like, for example, the whole USB stack I built for the USB versions of my devices, have 3 different versions of it. One that runs on macOS 10, one that runs on with a separate USB controller, and one that runs with an NatMel USB controller. And except for a few lines of code for sending the actual USB messages, the whole functionality behind it is the same. I can just like subclass it and instantiate it. The big advantage as well is that those mock objects I use on the host to like hide hardware features behind something. And I don't know if you've used C, you basically know the fdef hell. When you start to support different versions of your device, you're basically cluttering your whole code with ifdefs and diffs, and to like enable different parts. That's stuff you can do pretty easily by just subclassing and adding the stuff you want, or using multiple inheritance to have different features. What's pretty useful as well is it's just more readable to use object-oriented data structures. Like just a single linked list is just going to be add and remove. And in C, you will have all these kind of weird underscore kind of functions and passing the pointers all the time. So it's basically the huge advantage, and it just enables you to write code much faster, even on the embedded device. I mean, you can still use assembly if you want to, but you can integrate into your C++ as well. Which brings me, like, the bad thing about C++ is it's pretty bloated, especially with G++, which is a good compiler, but it just has a few things that don't work out very well. And that's going to be the next part of my talk, which is code optimization. There's 2 kinds of optimizations. Basically, you can optimize the speed so that the device is not very fast. It has like 60 megahertz and has 8 bits, so it's not very blazingly fast. What I found out is basically speed is not, most of the time, it's not really an issue. It's an issue when you're doing your latency and timing critical parts of your code, but basically the rest is you're not doing much. You're not doing crazy math functions on it. What's an issue though is if you use 8-bit, 16-bit, or 32-bit types for integers, for example. If you use 16-bit, the code is going to be 5 times as long